Well, good morning, everybody, or good afternoon, good evening, as the case may be. Very happy today to introduce our next speaker, Vladimir Sverak. Vladimir obtained his PhD at Charles University, where he studied under Professor Nečas. He graduated in 1986. He then did postdocs in Edinburg and at Bonn, until being awarded a professor position at the University of Minnesota, where he's been since 1994. Among his many prizes, he received the EMS prize at the first European Congress of Mathematics in 1992, and was an invited speaker at the International Congress of Mathematics in Zurich in 1994. He's been a distinguished McKnight professor at the University of Minnesota since 2000. And in 2017, he received an award in mathematics from the Neuron the Neuron Foundation in Prague. Professor Sverak works mostly in partial differential equations and has made important contributions to the calculus of variations. Today, he's going to give a talk in the open problem series entitled Some Conjectures That Seem Difficult to Prove. So we're very happy to hear about this today, and the floor is yours.
Thank you very much. I appreciate the kind introduction, and I would like to thank you for the invitation. It's a real honor to speak in the seminar. So let me start with a problem which I discussed some years ago at a very nice conference in Palo Alto, which was also the theme there was also computer-assisted proofs. So we have the three-dimensional Navier-Stokes equation in R3, and want to solve the classical Cauchy problem in R3 times 0 infinity with initial condition U0. And I would like to emphasize the Newtonian aspect of the model, right? So one way to view it is that the initial state U0, initial condition U0, gives the full description of the system at time 0. And our task is to predict the behavior of the system for the future. So that's what the equation should do, right? The initial state plus the equation of motion should predict the future of the system. And if we want to have an unambiguous prediction, that's the same as uniqueness. That's the point of view emphasized by Ladyshenskaya, that the main point for Navier-Stokes equation is to prove uniqueness in some suitable class. Because then if you have uniqueness, the equation does its job. It gives you unambiguous prediction of the future. If you don't have uniqueness, then the problem is incomplete. The equation, the description by the equation is incomplete. So does the Navier-Stokes equation give an unambiguous prediction of the future from the initial data? We don't know. It's not so clear. So in this first part, let me discuss some of the issues. So the only coercive estimate which we know for the three-dimensional solutions, for general three-dimensional solutions, if we leave some special classes of solutions, but for general solutions, the only coercive estimate is the energy inequality, a very natural identity from the physics point of view. Energy at time t2 plus energy dissipated between time t1 and t2 is equal to energy at time t1. So this by itself does not give uniqueness, but if you use the proof for the difference of two solutions. So the proof is very easy. You just multiply the equation by u, integrate by parts. This is what comes out. If you do this, so we take two solutions, u and v, look at the difference, w, and do the same procedure for that. We get this identity here, which is similar, except we have this extra term. And if this term is reasonable under some assumptions, it's not hard using Grunwald inequality to get uniqueness for classes of solutions which are sufficiently regular. And in fact, if you are careful and you optimize this argument, right, going through the proof, trying to use the least amount of regularity on u at each point, then you get the best known result about uniqueness. So for smooth solutions, we have uniqueness. Now, when we do finite dimensional approximation, so which is presumably what we do in any type of numerics, the simplest way or a very simple way is to take a finite dimensional approximation in the space of divergence-free field, and then project the equation on the divergence-free field, and then you get an ODE. If one does it in the right way, you still have the same energy identity as before, and this time it is an ODE. We have a coercive global estimate, so we have both global existence and uniqueness. So of course, at the level of a specific approximation, say here in the space Xn, we do have both global existence and uniqueness. And the question is, what happens as n goes to infinity? So the solutions which are obtained in this way are usually called Larrey-Hopf solutions, Larrey-Hopf weak solutions sometimes. So Larrey used a slightly different approximation in 1930s in his paper. One could say a better approximation in some sense. And Hopf then used more or less this approximation in a bounded domain in the 50s, and they studied the limit as n goes to infinity. So let's first discuss a situation where everything goes well in 2 dimensions. So in 2 dimensions, we have a perfect picture, at least. Of course, there are still many interesting problems, but from the point of view of existence and uniqueness and predicting the future, the situation is perfect. So it's enough to, if when we work with energy inequality, it seems like the natural assumption on the initial datum is just that the energy is finite, that U0 is in L2, right? That's what comes out in the energy inequality when you look at this finite dimensional approximation. On the right-hand side here, you have L2. So these are projections to L2. So if the initial condition is in L2, this stays uniformly bounded. So that seems to be a very natural condition. And indeed, in 2 dimensions, everything works with this condition. You don't need anything else. So you have initial condition U0, then there exists a smooth solution. The initial condition does not have to be smooth, but it immediately becomes smooth and stays smooth. And any reasonable approximation by these spaces Xn, which you choose, it converges to the solution. In particular, the limit of these approximations is independent of the choice of these spaces as long as they satisfy some reasonable assumptions. And everything is based on energy inequality. So in this case, just Galerkin approximation, energy inequality work perfectly, and you get exactly what you want. So what about 3 dimensions? So I will distinguish 2 cases in 3 dimensions at first. First, I will assume that we have some additional smoothness for you, right? It looks, I will discuss later the question why we need additional smoothness, but let's first assume that we have some additional smoothness. It does not need much. For example, L2 intersection L3 is enough, right? A little bit of extra smoothness beyond L2. Then the same situation which we have in 2D is true up to some time, which depends on the initial condition, right? So we can prove the same. There is some time, say, which here I call capital T, where we have the same situation as in 2D. There is a unique solution, and our approximations converge to this unique solution. But we cannot rule out that a singularity will do, right? Whether or not this happens, that's a millennium problem. But after the singularity, our solutions, our approximate solution, xn, are still well defined and good, right? These are defined globally. And if we choose a suitable subsequence, then we can, they converge to some solution, which is good most of the time. There is a big open set. The complement is has some one-dimensional Hausdorff measure 0. So it's really the set of potential singularity is very small, where we have still the same situation as here, except we have to choose a subsequence, right? We don't know that the original sequence will fully converge, but if we choose suitable subsequence, it will converge everywhere except at this possible singular set. I should say that this exact statement, okay, I'm a little bit maybe exaggerating here because it depends on how exactly you choose the approximation, right? This statement, one can get into open problems with the choice of the approximation and so on, so that you want this to be true, but I don't want to get into these technical details. So I simply assume I choose the best possible approximation, which in this finite dimensional approximation. And so the situation modulo this set of possible singularities is still very good, except you have to pass to the subsequence. If somebody else chooses a different subsequence, maybe they will converge to a different solution. And in other words, after the first singularity, the equation loses its ability to predict the future. There is no prediction of future after the first singularity, even though the solution it gets nice again and everything, but you lose uniqueness. And this is, at least we don't know how to prove uniqueness, even if you have a singularity at one point. Okay, the mildest possible singularity you can think of at one point, it already destroys uniqueness for all the futures starting from that point. So in this sense, as far as we know today, from what we know, we cannot say that the equation predicts the future. It doesn't. Based on what we know, we cannot say that. So here, that was the good situation when U0 was smooth, right? And I remember when I saw these problems for the first time as a graduate student, it always bothered me. Why do you need here this extra assumption that U is smooth, right? It doesn't look natural because everything there just points to energy inequality. Energy inequality is the only thing you know when you do the finite dimensional approximation. It's exactly what you need to prove uniqueness. And it seems like the right theory should be based on this energy inequality and the initial condition in L2. Why do we need this extra assumption? It seems somewhat artificial, technical, right? But there, as you will see, there are strong arguments that this is not the case. There are strong arguments that if you only assume the initial condition in L2, then the equation does not predict the future even for a millisecond, right? It can get wrong right from the beginning. So this seemingly natural assumption, I mean, psychologically, it was very difficult for me to overcome this, that this is not enough. You cannot work with U in L2. And I would like to, propose that maybe you can prove this with a computer-assisted proof. Okay, so I'm of course it may be a long shot. Okay, but at first it looks surprising because that's exactly what you don't want to do, right? To do some calculations where you have maybe some singular behavior and so on. But the key point is that as you will see, that the arguments rely on working with smooth functions, right? Everything can be reduced to working with smooth functions and properties of smooth functions in 2 dimensions. So ultimately, it goes to a 2-dimensional calculation with smooth functions. And what is the target claim? The target claim is the following. I have a function in L2, U0, which is in fact much better than L2. Okay, it's compactly supported. It's singular only at one point, where the singularity is like -1 homogeneous function. It's in 2 dimensions, it's like 1/x, okay, except it's a divergence-free field. And the smoothness away from the singularity, it's exactly the same as that of the function. So it's a quite nice function, right? Which is almost in L3. So not quite in L3, but almost. And then you have 2 sequences of smooth functions converging to it. Okay, one which we denote U0n, and that produces a smooth solution in this strip, and the other one V0n that produces also a smooth solutions. Both of these initial conditions converge to U0 strongly in L2, but the solutions, the limits of the solutions they produce are different, right? So that's exactly the situation that when somebody chooses one Galerkin approximation, they produce one solution. Somebody else chooses a different approximation, they produce a different solution. And both of them are perfectly legitimate, okay? In fact, you can produce solutions which are related by a symmetry, 2 solutions which are related by a symmetry. So if one would think there is some selection criterion, as long as you have a strong symmetry, it should apply. If it applies to one, it should also apply to the other. So it seems that simply the equation at the level, unfortunately, at the level of L2, which seems to be so natural, does not predict the future. And this, of course, if we go to the original picture which involves the millennium problem, where we start with smooth data, if you were able to prove uniqueness with L2 initial conditions, then of course we probably would be in a good situation here too, right? Because there is partial regularity, so the solution is always good on quite a big set. In particular, as you approach capital T, there is a nice blow-up profile. And due to energy conservation, this blow-up profile is in L2, right? So you have some initial condition which you can start with here at the blow-up time. Maybe it is singular, but it's still in L2. If there was uniqueness in L2, you could just continue uniquely from here, and you would see that the equation does predict the future, right? So this situation with potential non-uniqueness in L2 it becomes very relevant as soon as you have a singularity. So when you hit a singularity, you encounter exactly the same issue, which here you encounter them immediately, even before you start the evolution. So let me very briefly mention the reason for the difference. There are between 2 and 3D. There are many reasons, of course, but one of them is related to the scaling symmetry and how the function 1 over x behaves with respect to L2. So we have this scaling symmetry for the equation, and in 2 dimensions. Now let's forget time. Let's say assume we are at t is equal to 0, and we scale this function. So we just look at what is happening in space. In 2 dimensions, this doesn't change the energy. If you scale the function like this, the energy does not change. This function 1 over x, which will be important for us, right? I mentioned that the singular solution has this type of behavior. This function in 2 dimensions, it just misses L2. In fact, the numerics suggests that if you are allowed to take functions singular as this in 2 dimensions, so that would be, say, if you were in dimension 2 plus epsilon, or if the energy was with power 2 minus epsilon, then you can still produce non-uniqueness, right? So here you are just at the borderline in the borderline case, where everything just works out so that you can prove uniqueness. In dimension 3, if you do the scaling, you notice that, so if let's think about lambda as large, and then, so the solution becomes very large in the L infinity norm. The frequency, the Fourier spectrum goes to high frequencies, right? If lambda is large, but the energy decreases. So the scaling, you can, so that's the whole problem, that somehow the energy that sending frequencies to high modes in a way compatible with the equation and losing energy at the same time is compatible in 3 dimensions, whereas it's not compatible in 2 dimensions. So what's the idea of proving this by using smooth functions? The idea is to look at forward self-similar solutions. So those are solutions of the equations of this form. And if you want that there is some reasonable limit as t goes to 0, you find out that asymptotically at infinity, the function has to be -1 homogeneous, right? Just if one takes t to 0, then x over t goes to infinity, and there is 1 over t here, and you have to have some cancellation to produce a reasonable limit away from 0, and that comes down to the fact that the function, essentially the leading term has to be -1 homogeneous at infinity. A good cartoon picture to think about is, say, if you replace u with scalar function, is this type of a function, right? If u is a function like this, which is asymptotically -1 homogeneous at infinity, and you substitute this expression to it, you get this function. You see, it's essentially like a smoothing out of this function 1 over y, right, with scale square root of t. So that's essentially the picture which we have. So we want to look at these solutions. There is a PDE. If you substitute these solutions, you get a PDE, which is essentially Navier-Stokes with this term. There's an extra term coming there from the scaling. And this is a good term. This is, in some sense, it doesn't look very pleasant at first, but in fact, it is a good term. It makes the problem more similar to finite domain. We are in infinite domain, but this makes the problem more similar to a finite domain. And our task is to find a solution of this, which has a given asymptotics at infinity, given by this -1 homogeneous function A. And the idea is that this solution of this problem is not unique as long as A is not small, or for suitable examples of A. So this already deals with smooth functions, right? There is no singularity. Now, to study non-uniqueness, a sufficient condition for non-uniqueness is if we get some information about the spectrum of the linearized operator. So we linearized the operator at this. Okay, this is linearized the equation at this. This is the linearized operator, and by some theory and relatively standard bifurcation stuff, it turns out it's enough to show that the spectrum of the linearized operator crosses into the right half plane to the points with positive real part in the spectral plane, in the complex plane. Right? That's what this is sufficient. Plus, one needs some non-degeneracy assumption, but those are usually satisfied. This is sufficient to prove non-uniqueness. So to get this result about non-uniqueness, if we combine the calculations with some theory, it's sufficient to establish this spectral property that the spectrum of the linearized operator crosses into the right hand into the right half plane here, crosses the imaginary axis. Existence of U is known. You can prove that using some topological argument. So what we need to study numerically is the spectrum. Now the calculations of the spectrum have been done. This was done by Julien Guillot. He did the calculation, and you see that the spectrum indeed crosses. So this we chose a particular initial condition here. Okay, the sigma. So there is some specific function here, which we take fixed and then multiply by sigma. So you can think sigma as a Reynolds number or something like that. And as sigma is equal to 0, you have the spectrum is explicit. It's a known operator, Ornstein-Uhlenbeck operator, where you can calculate the spectrum explicitly. And it's 3 halves, 2, 5 halves, 3, and so on. This picture, all this is done numerically. There is no input which would use the explicit explicit formulas, but you see they are reproduced quite well here. And you see that as sigma is approaching about 300, just below 300, the spectrum indeed crosses, indicating non-uniqueness. So there are some. These are the bifurcation which you have there is a standard pitchfork bifurcation in the presence of Z2 symmetry. So the condition which we had is it's symmetric with respect to flipping the Z-axis, right? If you take the mirror symmetry with respect to Z is equal to 0 plane, it's the situation is symmetry with respect to. So you have this Z2 symmetry, and the bifurcation comes exactly as a breaking of the symmetry, and there are some kind of hand waving arguments which you can make to that this is indeed reasonable, why the solution might lose symmetry, might lose uniqueness there in this setting. So let me compare this to an analogous problem, which I think probably it is harder. Say for computer-assisted proof, my suspicion, I may be completely wrong, of course, but I think it may be harder because you don't have this extra term there, which in the Ornstein-Uhlenbeck operator, which helps you, I think. So let's consider the problem of a flow around a ball, classical problem. Stokes already considered it as one of the first application of the Navier-Stokes. So we want to solve the steady state Navier-Stokes equation with a given value of velocity at infinity, right? And so the theory developed by Larrey says there are solutions, and the issue this time will be stability. We want to make it as similar as possible to the previous spectral problem. So stability of this flow. So for small velocities infinity, we have the laminar flow, which is stable. The spectrum is separated from the imaginary axis to the left, like here. You start increasing the velocity. Every textbook tells you that the stability will be lost, and at some Reynolds number, the flow becomes unstable, right? Nobody doubts that this is the case. You see it in experiment, you see it in numerical calculation. For example, I chose this paper from 1989, and you can see that they calculated the spectrum, and they see that the stability is lost at Reynolds number 175, which, by the way, when you get to this stability issues, so in our calculation, when we did the calculation for the non-uniqueness, the viscosity was set to 1, right? So the Reynolds number in that case was essentially this parameter sigma, which we had. So here, if you set viscosity equal to 1 and the radius of the ball is equal to 1, then the Reynolds number would be the velocity at infinity. And you see, it's not, I mean, it's not so much different from what we have, right? That's pretty typical in these stability issues, that these values of Reynolds numbers, say of around 100 or in the hundreds, it's where the stability is lost. So here you have, you see these two. Here the loss of stability is different. Here it is due to the Hopf bifurcation, right? The solution, the first sign of instability, you see that the solution starts oscillating. So I don't think you will find anybody who will doubt that this is the case. But as far as I know, it's not been proved rigorously. There is no theorem which would, so what would you like to have? You would like to have a statement that, say, if you have this flow around the ball, that for sufficiently large Reynolds number, the flow becomes unstable, right? That would be an ideal, maybe without specifying the exact threshold, but let's say for sufficiently large Reynolds number. I don't think this has been proved. And I think, not that I know much about it, but my suspicion is that if one wanted to do a computer-assisted proof, then the previous problem maybe is a little easier than this one. But because here the problem is that somehow the behavior at infinity is inhomogeneous, right? You have this wake region where you have a different situation in front of the ball than in the back of the ball, and somehow one needs somehow to manage the situation at infinity. So I think that might be easier in the previous case, but okay, this is just a speculation. So the above, what I discussed, it does not address anything about the question where you start with smooth data, right? It at best, it gives you the answer to the problem, or it will show you that unfortunately, if you only start with U0 in L2, which at first seems to be like a great idea, just to focus on the L2 theory because everything else is artificial, seemingly, that this is not such a great idea, that it simply doesn't work, and there are counterexamples. So that's what the previous would give you. But it would not address the question about what if the equation predicts the future from the smooth data. That would require the solution of the millennium problem. But there is a model equation where this seems to be possible to address. It's an interesting model equation, the complex Ginzburg-Landau equation, which looks like this. It's a nonlinear Schrödinger equation. The unknown function is from R3 times some time interval into the complex numbers. And epsilon is equal to 0 is just the nonlinear Schrödinger equation. And in this talk, I will just talk about this as a model equation, which mimics some features of Navier-Stokes, but it is a legitimate equation in physics, not a fundamental solution, but it's some kind of like describes some envelopes or something like that. But it has a physical meaning. So everything which I said about Navier-Stokes can be done for this equation. So there is a energy identity. You can prove exactly in the same way, right? You can have Galerkin approximation and so on, and you can ask about non-uniqueness. So that's my main point, that in the rough way, this is similar to Navier-Stokes, even though the nonlinearity is quite different. But at the level of, okay, we have Galerkin, we have energy identity, and we want to pass to the limit and so on. This is essentially the same. So I learned about this equation from a paper by Bartuccelli and co-authors, where they developed Lerey-Held theory, and they introduced also some deeper results. For example, the result that for sufficiently large epsilon, you don't have singularities, which does not have an analogy for Navier-Stokes. And then Chiado and Yan prove partial regularity, just as for Navier-Stokes. So everything we said about Navier-Stokes, like if you have your Galerkin approximation, you can pass to, it exists globally, you can pass to subsequence, which would converge away from a very small set to a nice function and so on. Again, Dave Livermore, he also made more analogies to turbulence. And it seems that that for this particular equation, the scenario which I was discussing before, so the scenario which is bad for the equation, right, in the sense that the equation does not predict the future, you can it should be able to establish it, or at least worth trying. And it might be doable by a computer-assisted proof, because it has a big advantage over the Navier-Stokes equation, because you can work in 1D, because you can consider radially symmetric solutions, so that you will have just one space variable, one time variable. And the scenario would be exactly the one which I was mentioning. You start with smooth data, compactly supported. Okay, for a while, say the situation will be good up to a certain time. Then a singularity develops. Okay, the solution, the weak solution, you can continue, but unfortunately, you will have non-uniqueness. What happens after the weak solution, it will depend on how you choose the Galerkin approximation, which subsequence, and so on. Okay, so in this case, it seems, I should emphasize that this has not been proved rigorously, that the equation does not predict the future, and there does not seem to be any easy way to fix it, right? For example, in the theory of hyperbolic systems, we have also this phenomena, like Berger's equation does not predict the future if you do not introduce some additional criteria like entropy dissipations. But here it seems to be quite worse. I don't think there is an easy way to fix non-uniqueness, and maybe one just has to accept that these equations simply are incomplete, that they do not predict the future. So the problem here for this equation is essentially the same as before for Navier-Stokes. The only issue is to produce the singularity, right? If we could produce the singularity for Navier-Stokes, then we would know what to do. And here it is the same, except you have a much better understanding how singularity can be produced. This is related to the fact that people know how singularities can be produced for a nonlinear Schrödinger equation. Even though I think this direction of like proving things by computer-assisted proof, even for nonlinear Schrödinger equation, it would give new result because they are important. What can be proved rigorously for nonlinear Schrödinger about this type of singularities is limited to some special sets of parameters which are closed to the critical case. And for example, the three-dimensional case, as far as I know, is not approachable by paper and pencil proofs at the moment. So we would like to look at singularities like that, right? It's kind of similar idea as before. Before we looked at forward self-similar singularities. Now we look at backward self-similar singularities. If we did not have this guy here, the red term here, it would be just straight backward self-similar singularity, the naive self-similar singularity, if you will, but that doesn't work. This is an important. This term here is a very important twist here, introduced essentially by Zakharov in connection with nonlinear Schrödinger. And you can use the same, okay, so one has some equation for this, for this profile Q, okay, here is the equation. And using the fact that you have to have a good limit as say t goes to capital T, you know that it has to have a certain prescribed behavior at infinity, right? So the task is show this has a solution with this prescribed behavior at infinity. This is the original paper by Zakharov, and then there is an influential paper by Landmann and co-authors where this was for the nonlinear Schrödinger equation. This was studied rigorously. What is known rigorously for nonlinear Schrödinger, there is, I think, one of the best results is a recent paper by Barry, Martel, and Raphael, where essentially they can prove what we would like to prove in our setting for complex Ginzburg-Landau, which of course includes nonlinear Schrödinger. We would like to cover epsilon is equal to 0. So they can prove it in dimension 2 plus epsilon for radial functions, right? But we want to get to 3. So 2 is the critical case, which is relatively well understood. And so if you use very clever perturbation theory, you can get a little bit away from the critical case for completely rigorous proofs. But 3 is too far away. 3 is just deeply in the supercritical regime, not approachable by, as it seems. You should take it. Okay, I have not seen the latest developments on this. Okay, so solutions, I think I already said that solutions of this form probably do not exist. And there is a lesson, just as a side remark, there is a lesson from this also for the Navier-Stokes equation, right? If one tries to compute Navier-Stokes singularity of this form, an idea going back to Larrey, it doesn't work. You can prove rigorously that you cannot have Navier-Stokes singularities of this form. But just as for the complex Ginzburg-Landau, you can. So this is based just on the scaling symmetry, right? But there are many other symmetries, like for complex Ginzburg-Landau, you combine the scaling symmetry with the gauge symmetry, right? Multiplying this, that's how you get these. How you can think about these singularities. So for Navier-Stokes, you can think in similar terms. Let's compare the scaling symmetry with, say, the rotational symmetry. So you get a slightly different singularity, and that is open if such a singularity exists for Navier-Stokes. So what comes out if you want to solve this thing for complex Ginzburg-Landau? If you look at so this is the equation. Okay, which you want to solve, say, on 0 infinity. And so the first, and we have a prescribed behavior at infinity, right? So we have it, so we can neglect in the first approximation, let's neglect the nonlinearity and let's just look at the linear part at infinity. And fortunately, as it often is the case for these self-similar solutions, the linear part is given by known functions. If you do the right change of variables, you get so-called confluent hypergeometric functions or Kummer functions, which are well understood in the complex plane. So the point where we did this some years ago with Peter Plakach, and we of course were not sure what will happen if you make epsilon positive, but when we got convinced that that you can really deform it into positive epsilon, when we realized that so you're looking for the right solution of the linearized equation of at infinity, right? And you do the change of variables, which corresponds somehow to rotation in the complex plane. And the theory of Kummer functions is known in the complex plane. And you see that you have a good solution. Even after you introduce epsilon, you have a good solution at infinity, which satisfy exactly the right properties which you have. And then you can do a perturbation theory and show that you have a good manifold of solutions at infinity, right? For which you get The Navier-Stokes equation, if you do numerical calculation, it doesn't seem it wants to blow up, right? Like, for example, these singularities for complex Ginzburg-Landau equation, they seem to be stable. So once you get into a certain regime, you are attracted to these singularities. Even from generic data, if you do numerical simulation of like a two-dimensional, for example, or so, you seem to be attracted to these radial singularities. So these seem to be stable objects. So for Navier-Stokes, I think, based on evidence which we have, I don't think there are any stable objects like that. So it's quite conceivable that that singularities still might exist, but all of them are probably unstable. So for generic initial conditions, so one can speculate that for generic initial conditions, you will have a global smooth solution, which then will give you uniqueness. So in some sense, maybe if this is the case, you can have both worlds, so to speak, right? That most of the time, the equation will predict the future, because for a generic initial data, you will have a smooth solution and uniqueness. But in some exceptional cases, maybe non-generic, you will hit a singularity, and then it will produce this non-uniqueness, which we have. And in those very special cases, the equation will not predict the future. So that's the most consistent story with everything we know, as far as I can tell. But of course, it's a pure speculation. Okay, that's all I want. Thanks.
Okay, thank you very much for wonderful talk. We'll now open up the floor for questions. Anybody have any questions? Please just turn on your mic and jump in.
Well, if I may start, so you talked about these spectral properties which you need. So what do you really need? Do you need, for proving such things, do you need a global picture of the spectrum, or you just need some eigenvalue which is contained in some specific part of the complex plane, or what is precisely needed?
So what is known is that for, say, small, so I have this parameter there. So okay, let's go to where was it? I think I need to go up.
Before,
yeah. Here. So it is known that when this parameter sigma is small, that everything lies left to the axis, right? You can prove it rigorously. And there is some continuous spectrum which will stay there, that also you can prove rigorously. And so so in the region, say, between this line beyond which you have the continuous spectrum and the imaginary axis, you may have isolated points of the spectrum. And so what we need to show, and we know that for sufficiently small sigma, all these points lie to the left of the axis. So what you need to show that some of these points will cross.
Cross means when you increase the parameter.
Yes. Yes, you start increasing the parameter, and you need that. Strictly speaking, you need some non-degenerate crossing, right? You need some. You don't need just cross, but one needs some non-degeneracy condition. But the non-degenerate, I think it will be generically satisfied, right? That the main thing is just you need them to cross.
Yeah, but cross means just to prove that there exists some sufficiently large sigma. That's right. Where eigenvalues are on the right complex half plane, right?
Exactly.
So all you need is to show that there exist eigenvalues in the right complex half plane.
That's right.
And of course, there are methods for doing that, for computer-assisted methods.
That would be great.
At least in principle. I must be careful.
That would be great. Yeah.
Actually, also regarding this, I mean, would it be possible, maybe also asking Michael, but to set up a zero finding problem, because that would kind of emphasize that you are exactly on the imaginary axis. And if you can prove that using a contraction mapping, then somehow you would know that for a small perturbation, it has to cross, because otherwise you would not have a contraction. Would there be a way to identify this phenomenon as, say, a locally unique zero of a nonlinear map? Because we do that for half bifurcation. So if I want to show the existence of a half bifurcation, I can set up a zero finding problem that I solve using a contraction mapping theorem. And because of the contraction, we know that small perturbations will imply that we have to cross because of the contraction. So do you think, maybe both to Michael and Vladimir, do you think that such a zero finding problem could be also set up?
I think what you're just saying is that by the contraction mapping principle, you automatically prove the non-degeneracy, which Vladimir was talking about. I think that's precisely what is needed. Yes.
But what kind of zero finding problem so this is the linearization at what again? Of a large solution which is not known analytically. We would have to solve for it, no?
That's right. So, but that's not the problem. I think it seems to me like the main issue somehow is still that the domain is infinite. You know, that somehow one would have a very good, which probably may be doable for complex Ginsburg-Landau. So one would have to establish good properties at infinity of this set solution, right? So that you can start from some finite, which numerically seems to work well. That if you do your calculation on a domain of one radius and then you double it, then you see you have some good asymptotic behavior of the solutions. But to get everything, you know, the size of the constants and so on, that I think, to my mind, that would be, I don't know if there are any examples where people do things on unbounded domain where you would somehow treat the manifold of solutions and then start from it in some finite point.
We did problems on unbounded domains, but with decay. So where you know that the functions are globally in some Sobolev space or so.
You have decay here. Theoretically, you have decay here.
Yeah, then it's so so decay means belonging to some LP space or maybe even some Sobolev space or.
So here you have pointwise decay, like you know that so solution decays like 1 over x or something like that.
Oh, okay.
And the derivative like 1 over x squared and so on.
At least I think it would be worth to look at that in more detail.
That'd be great.
Other questions?
Well, I actually have one. So you mentioned this, the looking for the degree theoretical argument for this F, which is the F coming from the matching condition of the solution starting from Q prime at 0 to be 0, and at infinity it goes to 0. So I don't know, could you go back to this slide where you have this non-autonomous second order ODE on the real line?
Let's see, where was it? I wonder where it was.
I think here. It's 26. Yeah. Oh, no, not 26. Yeah, this one. So the equation themselves are like non-autonomous second order ODEs on the whole line. And now you're proposing an approach based on degree theoretical argument with this F. Yeah. But so from our perspective, it may be easier to just solve like a connecting orbit, which is somehow symmetric at 0, and then at infinity, we have the second order non-autonomous problem. And so in some sense, the idea here is really to prove that you have a solution going from, which is even at 0 and then goes all the way to plus infinity, and it solves the equation, right? And Yeah, I mean, if it was me, I would try to set it up as I would try to parameterize a stable manifold at infinity, and then to solve a projected boundary value problem with the right hand boundary condition in the stable manifold. And we would have to do that for the non-autonomous, maybe by augmenting the dimension of the system to make it autonomous, maybe in 4D or something. But say the conjecture is about the existence of that solution, or that's just
Yes.
the step? Okay, the existence, only the existence.
Yes, yes.
And it doesn't matter. I mean, your approach based on the degree theoretical argument for the F. I mean, if it was another approach, you wouldn't mind, as long as you have the solution.
No. I mean, this is what I thought about, when we were doing. So what we really were doing when we were calculating it, we were doing a shooting method from some point here, from some, I don't know, like 50, or it turns out it's quite, I mean, once you get to 30, it doesn't really matter if you start from 30 or 100. It's very well behaved, okay? And we were doing a shooting approach from here all the way to 0, okay? And it already behaved quite well. But there are, I was thinking about this because for the rigorous approach, you have, if you look at the ODE, you have some singular coefficients at 0, right? You look at so I was thinking that maybe one can start shooting also from here, and then you would be matching, because you have a better handle on these singular coefficients. So and then one would do the matching in some harmless region here, but numerically, so there is one reason why to do it this way, shoot all the way to 0, because you have this second solution of the ODE, right, of the linearized ODE, and this has very nasty behavior if you go in this way. Okay. So if you want the other solution not to kind of wreak havoc on your calculation, it's much better to go this way.
Okay.
I think here you have the additional advantage that you don't need to enclose the stable manifold by numerics, and computers is the proof, but you have it already parameterized in terms of these Kummer functions.
Mm-hmm. Right.
So I think that part would even be easier. You only need, so the parameterization of the manifold is simple here, is my impression, and you just need this connecting orbit. Just okay.
Right. I mean, conceptually, I think conceptually yes, but of course to do it so that, I mean, with all detail, that still, I think it still would be interesting.
Yeah, I mean, what I would do is that I would take your, I mean, it is on the slide before that you have the ODE, the non-autonomous ODE.
Sorry, maybe on the next one.
Oh yeah, this one. So this one, well, what I would do would be to say make it polynomial, because now it's non-autonomous and you have this 1 over xi, so which itself satisfies a simple nonlinear ODE. So I would define a new variable and I would make this ODE a polynomial one say in R4, and then I would try to kind of solve a connecting orbit for that problem, which is, I mean, that would be what I would try to do. But we often do these things when we have non-autonomous or when we have difficult nonlinearities to kind of introduce these extra variables. Mm-hmm. If I define Q1 to be 1 over xi, then Q1 prime is something like minus Q1 square or something. And then I append that to the problem, and I make a new problem, which is now polynomial, and I try to solve a connecting orbit for that new polynomial, say ODE in R3 or R4. And then there we have the nice parameterization method. And this is what I would do, but maybe people have different ideas. Yeah.
Maybe also I have just to confirm something. You said there was some problem at 0. So this is exactly what you meant with this 1 over psi at 0 is the singular term, right?
Right.
Okay.
Right.
But since you assume q prime of 0 is 0, I mean, it's probably, I mean, it looks singular, but it's not essentially singular, right?
That's right. That's right. I mean, that's why I was thinking that if you start from 0, you can somehow explicitly build it in, right? And
okay. So do something local close to 0, and then you.
Right.
JB and Jean-Philippe, you've done that for something else, right?
Yeah, right. I mean, you could even, this is what we call removable singularity. You could do a Taylor expansion at 0 and then just solve a small segment from 0 to delta, and then remove the singularity with Taylor series, solve the ODE with that, and then, I don't know, do a connecting orbit. I don't know. I mean, things like that, right? I think we have tricks, but.
I think this singularity, this is just the same as for any problem where you look for radially symmetric solutions of a PDE.
Yes. Probably if you do some clever substitution, one can remove the singularity.
Yeah, absolutely. And once you have this say connecting orbit or this solution, what do you do with it? I mean,
so if you have this, then you know there is a self-similar singularity. So you have your large object, say at least for the you have your singularity, which I think, for example, even for people in nonlinear Schrödinger, as far as one would have to check, of course, I may not be completely up to date on that, but as far as I know, as far as I can tell, that this does not exist, a rigorous proof of this solution.
Okay.
And then the next step would be to do the spectral analysis around this solution. I mean, but that's much simpler. What you need for the spectral analysis is simply just the so the blow-up profile will be exactly a times this psi to -1 minus this complex exponent, right? So this calculation gives you what a is, what the value of exactly what the blow-up profile is, and then one does calculates the forward self-similar solution from that and the spectral analysis.
And the spectral analysis, this crossing, so for the simplest case would be to linearize about that solution and then look for the crossing for the.
It's similar for Navier-Stokes. So you calculate the forward self-similar solution. This time one can just solve the ODE starting from here. Okay, and then one does the spectral analysis around that, just as for Navier-Stokes.
By spectral analysis, you mean that you just have to calculate such crossings, or do you know more about it? Do you need?
So you the same as for Navier-Stokes. You know that the spectrum is on the left, and then you need to show that there is a crossing.
First sight, it looks doable by computer system.
Yeah. Well, at least for the radially symmetric complex Ginzburg-Landau. Yes.
Yeah, that sounds great.
Okay, can we get more details in order to think more seriously about this? So, I mean, for example, we can download your transparencies from your webpage, right?
I can send the transparencies, and on this complex Ginzburg-Landau, we have an old paper on the existence of singularity with Peter Plekach, which is on the archive. That's where I took the pictures. But for the spectral part, for the complex Ginzburg-Landau, that has not been written yet.
I see.
So we are hopefully it will be written at some point, not too far away. But the Navier-Stokes work has been written. So this is.
So I would be specifically interested in these spectral questions, right? Because I have some method for that.
Okay. So for complex Ginzburg-Landau, that has not we still have to write this up. For Navier-Stokes, it is written. It's on
right.
the
archive.
Of course I can send the preprints.
That would be great. If you send them to Jean-Philippe, then he may.
I will send him the links.
Yeah, that would be great. And also but the spectral analysis requires really the profile first, right? That's kind of in this picture, the whole profile, you need it to verify anything about the spectrum, right? That's
you don't really. So for the Navier-Stokes, yes, you need this forward subsimilar solution. For complex Ginzburg-Landau, what one needs is essentially the forward subsum. So I have not really discussed the forward subsimilar solutions for right. One needs the analogy of the forward subsimilar solution but that's relatively easy, because that's just amounts to solving an ODE, an initial value problem, and then somehow the behavior of infinity, the equation takes care of itself, so to speak, for the forward subsimilar solution. So maybe I should write even before we write the paper with Julien on this. I can write some short note on that. Which would explain the spectral problem. So what one needs for essentially, so you calculate the self-similar forward self-similar solution, okay, and that gives you the blow-up profile, okay. The blow-up profile is given by constant times this xi to minus, right? It has a very specific form, the blow-up profile. It's essentially minus. And all you need for the forward self-similar solution is this constant, okay? And then from that, based on that, you calculate the forward self-similar solution, and then you do the spectral analysis around the forward self-similar solution.
Yes.
To me, the main issue is somehow if one can get a handle on this infinite part of the right, somehow to somehow deal with the fact that the solution is not on a finite domain, but on an infinite. So the question which will come up is how precise information one really needs to be able to close things.
Yeah, I mean, that's why I was mentioning the parameterization method developed by Raphael de la Llave and Caroline Fontisch, is because if somehow you make it so that you have even an autonomous ODE, then you can really parameterize this object with extremely high accuracy and then solve a projected boundary value problem where you impose that you're in the stable manifold. Maybe this Kummer function would be better, but the parameterization method to solve problems on the infinite domain, it's absolutely fantastic.
Okay.
But you said these decay like 1 over x. They decay like, so it's probably a parabolic manifold at infinity. So it's, again, there are tools, but this is probably going to be a little bit delicate.
Yes.
More than when we have exponential decay at infinity or something like this.
Okay, so let me send to Jean-Philippe all the preprint I have, and I'll try to write some at least. I mean, eventually, I hope we will write with Julien Guillot a longer paper on this, but at least to you know, some rough kind of notes on the spectral problem for complex Ginzburg-Lambda.
Well, we should really thank you again, because this has been a wonderful talk and obviously very interesting to everybody. And it really requires a lot of courage to come in and give one of these open problem talks, which we really enjoy. And so thank you so much again.
Yeah, thanks.
I appreciate it. Thank you. Thanks for listening.
Okay, so I'll be waiting for your documents, and I will share that with the crowd.
Sounds good. Thank you.
Thank you so much.
Okay, see everybody again next week. Thanks again.
Thanks.